In this video, I want to calculate a triple integral. It's the triple integral of z over a, where a is the solid inside the sphere, x squared plus y squared plus z squared equals 2, inside the cylinder, x squared plus y squared equals 1, and above the xy plane. So first we should draw a picture of what this looks like. So a is inside. So here's the positive x-axis, y-axis, z-axis. You have the sphere, and it's centered at the origin, and what's the radius? The square root of 2, right? So you have the sphere like this. Oh, maybe I should use a different color. It's centered at the origin, it has radius the square root of 2. So it's inside this, but it's inside the cylinder, x squared plus y squared equals 1. Okay, so this is going out to the square root of 2, right? So 1 is less than the square root of 2, and so you have the cylinder like this, inside it, so it's like this. And then it's going around like that. Okay, it's not very circular. So you have this part, and then above the xy plane. So you have something like this. So it looks like you have the top, which is spherical, like this. And then it's a cylinder. Okay, but the top is spherical. So that's the picture. All right, and it goes out to 1, right? So we need to figure out how to set up the bounds of integration, and we see that z is going from 0, so z is going from 0 because you have the xy plane, but it's going up to this top part here. And this top part is given by the sphere. And so you have z equals the square root of 2 minus x squared minus y squared, right? If you solve for z, it's this top part of the sphere, and you solve for z, you get this. So you have to integrate. So by Fubini's theorem, the integral that we want is the integral with respect to z from 0 to the square root of 2 minus x squared minus y squared, z. And then you integrate this over the region R, which you project onto the xy plane. So it's this circular region R. Okay, and so to do the circular region, to set up the bounds for that, we should use we should use polar coordinates. So it's dr d theta. Well, we have r dr d theta, and then r goes from 0 to 1, and theta goes from 0 to 2 pi. So when you have something like this where z goes from one function to another function, and then the region at the bottom is a disk centered at the origin, and you use polar coordinates for that, that's the triple integral is cylindrical coordinates. Okay. So now that we have set this up, well, actually, we want to replace x and y in terms of r and theta. So I have this minus parentheses, right? So that's the square root of 2 minus parentheses x squared plus x squared plus y squared. X squared plus y squared is equal to r squared. So this is going to be 2 minus r squared. make that a little bit smaller. So the setup is like this. And now it's time to do the integral. So the inside integral. Now notice that you cannot split the function. Oh, let me swap the r and the dz. You can't split this into a product of integrals because you have one of the bounds is not constant. Okay, so we need to do the inner integral of, well, we can move the r outside, and then you have dz from 0 to the square root of 2 minus r squared, and then that's going to equal r times z squared over 2 from 0 to root 2 minus r squared, so I just moved the 1/2 out. And then this is going to equal r over 2 times the square root of 2 minus r squared squared is 2 minus r squared. And then minus 0 is just 0. And before you do the second integral, we should distribute this to make it easier for ourselves when we integrate. So you get r minus r cubed over 2. Okay, now we do the integral in the middle. That's the integral of r minus r cubed over 2 with respect to r from 0 to 1. So this is going to equal r squared over 2 minus r to the 4th over 8 from 0 to 1, and that's going to equal 1/2 minus 1/8, which is 3/8. And then, since you have a constant, the outer integral is easy. We integrate from 0 to 2 pi, 3/8 d theta, and so you just multiply this constant by the difference, right? 2 pi minus 0, and this equals 6 pi over 8, or with 3 pi over 4. So that's the answer. So in this problem, it's cylindrical coordinates. Okay, it's basically polar coordinates except with the z. And once you set it up, it's pretty straightforward. You just evaluate each integral one at a time. Oops. You integrate each integral one at a time until you get that answer. And of course, you should get a constant as a result.